Hello guys, welcome back to the video. So today we are going to see problem number 1277 of LeetCode, that is count square submatrix with all ones. So here in this where the topic is recursion and DP. With the help of recursion and DP we are going to solve it, and in the video we are going to see two solutions. So let's get started and move to the problem. Okay. So in problem it is given a Mn matrix of 1 and zeros. Written how many square submatrix have all ones. So it's simple. We just need to find like how many squares we can make with that one of that given matrix. Okay. So let's take an example and try to understand like how we can find it. So here we can see. So initially if we have only one, it will be counted as one. Okay. And it will be counted as a one matrix of one length. And this is a two matrix. When we have four ones like this is a one. Okay. So first see with one length how many matrix we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So here we have 10. Next we'll see with two length how many we have. Okay. So this is one of two length, two, this is three, and this is four. Okay. So with two length we have four. Okay. I'll just erase this part. Okay, and then we're going to see the three length. Okay, so this one whole becomes a three length matrix. Three length, that is one. So if we combine all this, we get 15 submatrix with all ones. This is all 15, and this is also we counted in this one only. Okay, so we got it. What we need to find? Let's see like how we can find out. So if we see, only we get if we count every single one, we'll get this length of one number as 10. Correct. So next we will see how to find the second, the two length matrix. So if we see, if we're standing here, that is 1 and 0. I will just index it. 0, 1, 2, and 3. Okay, we are standing here. If we see right, if we see down, if we see diagonal, if it is 1, it forms a square. Correct. And we can say it forms a 1 square. Similarly we can do for others also. Okay. Yeah, and we can see with this method we can find the squares in a recursion way. You can see we're just calling the same thing again and again. So it's a pattern we found it. So but there is a problem in this. Like if we go and find the starting, means we are finding how many squares are starting with this index. Okay, and if we go ahead like this, there is a chance like we will be counting the duplicate ones. So yeah, I will show you with this example only. So if we count this one, okay, we will get a 1. Okay, 1 square of 2 length is 2 by 2. Again we'll call this to check if we can make a 3 by 3 with this. Okay, we'll call this, right. Okay, so we'll call this and we'll get, okay, 3 by 3 is also possible. We'll add 1, but in that we are missing this 2 by 2 also. Okay, and if we again come here, then it will be including it two times. So instead of this, what we can do is we can do a backward call. Backward call in the sense we will see if there are how many squares ending at this index. So we want squares ending at this index, not starting at this index. Okay, so for this I will make a dp here. Okay, we'll just make a dp and see. So for with 0 index 0, are we going to make any square? No, so it will be 0 only. Okay, then for 1 0 1 we have 1. So how many squares we can make here? Only one square we can make. Okay, then comes 0, then again comes 2, that is 1. How many squares we are going to make here? We are again going to make only one square because there are the ending square we are finding, not the starting. Starting we can make, but we are not finding that as of now. Okay, then again at this index also we are going to make one square. Similarly for index 1 and 0, we are going to make 1. because there is only one, because previous to that it is an out of bound. We'll go to minus if we go and see back, and here also is 0. Now when we come to index 1 1, okay, at 1 1 we will see like its up is 1, left is 1, but diagonal is 0, so we'll only make 1 itself. Okay, we can make only 1. Then we move to 1 2. Okay, index 1 2, this one. Okay, I'll just change the color so we'll see. Okay, and here it will be like we can make 1 by itself, and we can also see like it's up is 1, left is 1, and diagonal is also 1, so another one square is formed, so we can write 2 here. Similarly, when we doing for this, we can say, we can see that 1 is formed by itself, and we can have the other diagonals also. So here it is 2. Similarly, we will calculate for this. So for 2 and 1, it will be 1 only, because here there is a 1 0 that will not make a square, so it will be 1. But here again we'll find 2, and here, right, here we will find a 2 or 3. See, ending at this we can find a 9. Okay, we get a 3 by 3 array. Ending as this index, we get a 3 by 3 array. So how to do that? We'll write 3. Okay, so I've made a DP here, so I'll just explain how we can connect it and write in the form of code now. Okay, so first we saw that by checking the diagonal right and up, we can say that it is a square, first thing. Second thing, we computed all this, and we see that we are doing what, if we get a 1 here, we'll just taking the calling the upside, diagonal, and the left, and taking the minimum of it and adding it with 1, and we get a 3. Similarly, we are doing here also. But you see here, if we go, here we are, here we have already 1, and the minimum is 0. So 1 plus 0 is 1, like that. So hope you get the solution for this. Okay, we'll do here one more iteration, and let's see, we make a DP array for this. Okay, so here it is 1, so we'll be having 1 only. Here it will be 0, it will be 0, because we don't have any numbers above it, like diagonally up, left, correct? We are finding the squares, number of square ending at that index. Okay, so this will be 1, this will be 1, this will be 1. Okay, so for now this one, it is 1 here, and the minimum of is 0, so it will take 1, because here it is a 0 and it is a 0, so we'll just write 0, because we cannot make a square with 0, right? Okay, then for this index, we'll see here it is a 1, and the squares or the index surrounding it is also, the minimum is 1 1 1 1 minimum, so we can write 2 here, and we can write 0. And if we add all this, like 1 2 3 4 5 6 7, so we'll get a 7. And if you check here, here also the answer is 7. So in this way we are going to solve it. So let's get started. Let's go to the compiler and code it. Okay, so we'll take first a DP, a 2D DP. And if you guys want, you can stop the video here and try this solution by yourself. Like I've explained the concept and I'm writing it down, or you can continue with me. Anything is fine. Then we'll take int. Let's take this, remove this one as of now. Answer equal to 0. On length, I'm writing a +1 to handle the edge cases. As you saw that for the index 0 0, if we do a -1, we'll go out of bound. So for that, I'm just adding one extra here and making a DP a little bigger, so that we don't go and we can start from 1 directly, like that. Okay, sorry, I will be 0 only, and I should be less than matrix dot length. Oh, sorry, I wrote it here. I forgot to write the length here. 0. dot length. Okay, then yeah, I is less than matrix dot length I plus plus. We'll moving from 0 back for, again we'll write this loop only with the j. Okay, 6 of 0 dot length, and we'll be filling this dp array. We are doing nothing else here. Okay, we'll just make this j, this also j. Okay, yeah, and if matrix of I, how much j is equal to 1. If it is 1, then only we'll count, else we'll keep it as 0 only. Okay, it's 1, we'll do it. So in the example we saw that we are taking the dp of I plus 1. Here I've added 1 in the dp, right? So here, so I'll just do dp of 1 plus in everything while calculating it. J plus 1 equal to 1. So I've got 1, so I will add 1 plus math dot minimum. So I'll check minimum of the 3 calls. Okay, so whatever the 3 calls it is, I will see dp of. So first call will be I and j minus 1. Okay, comma dp of, oh sorry, again I'll do a math dot min dp of I minus 1 j. Okay, and also I will do dp of I minus 1 j minus 1. Got it? What I did here, I'm taking the upper one, the left one, and the diagonally one, and checking the minimum in the dp array and adding 1 to it and just storing it there. Okay, we'll just in dp of I plus 1 and j plus 1. And similarly after this loop, okay, I'm also be adding it into the answer dp of, okay, I have to add here only dp of I plus 1 j plus 1. Okay, got it? Yeah, this is done, and we'll just return the answer. So that's it. Okay, so we are done with the coding. So let's run it and see if it works. Okay, we're getting an except problem here. Matrix not length plus 1, matrix of 0 not length plus 1. Oh, this is not required here, sorry. Yeah, and something more we are missing. Let's check. I think other thing looks good. I think one more thing we're missing here. Okay, this one is missing here. Let's check the code again, okay? This one is fine. I don't think this is come here. This will come here directly. Also, I noticed one thing. Like here we are writing I j minus 1, I minus 1. So instead of that, we should write plus 1, because actually we are, see, this is a 4 by 4 matrix and we are standing here, suppose, but we are writing into this one. So suppose my I is 0, okay, and j is also 0, but I'm writing into this. So my I and j actually is 1 1, which I'm writing, and I should be finding these 3 blocks. So for that, I will write 1 minute. I will write j plus 1 actually, I plus 1, and ij itself, nothing else. Okay, now I think code will work. something j equal to 0, j should be a matrix of, oh okay, here should be a dot, sorry. So it happens with me also, the syntax errors. Okay, yeah, it's working fine. We'll try to submit it. Yeah, it's working. So I've just solved in front of you. So here the time complexity will be big of 1, sorry, big of mn, big of mn means rows and columns, and space complexity will be also same, big of mn. Because we are using a DP array of size mn and we are iterating through each and every element, means index of that matrix. Okay. So this we can also do recursively, that I will show you now. We'll try to solve it by recursion. But before that, we'll see like how can we do that in the recursive format. So to solving it with recursion, we'll also need DP also, but we'll see first how we'll solve with recursion. So we'll use the same trick like calling the upper one, the diagonal, and the left one every iteration. So what will the, let's discuss the base cases. Okay. So if we call it first thing, it should be not out of bound. So if we call for this, it will be out of bound. So I should be not less than 0 and j should be not less than 0. If any one is less than 0, then we will return 0, 0 itself. That will return 0. First thing. Second thing, it will be the element itself should not be 0. Correct? If this is 0, it cannot make a square anyhow. So second base condition comes like if matrix of I and j is equal to 0, then we will return 0. Okay, this is we are doing recursion. After we'll memorize it. Okay, so and this we are done. Anything else you can think of? Think this is fine. Then if it is 1, we will call for the three calls, that is upper call, left call, and diagonal call, and we'll return the minimum that we were doing in the iterative way. Same. Okay. So let's write the code for it and see. And in DP, we can say we can make a DP table also here. Okay. And in DP table, we'll initialize everything as -1. Okay. And if it is not, if it's computed, we'll return it. If it's not computed, we will just calculate and assign that DP of ij to that value. Okay. So let's go to and code it. So we'll try fresh one so that you guys can get it, the second solution also. So we'll write first df function for it. So public int, it will return in find. We'll write find as a name, int I, comma, int j, comma, and we'll pass the matrix also here. Matrix, oh sorry, matrix. So this is done. So if I is less than 0 or j is less than 0, we will return 0 itself. If matrix of I, sorry, it's not 0, I and j is equal to 0, again we will return it as we saw. Then we'll be having a dp array also, correct? And dp, or we'll add it later. Let's see what happens here. Okay. Then we'll have two calls, and t upper equal to find I -1, comma j, comma matrix. Okay, so we have like these three calls: the upper, the left, and the diagonally upward call. Diagonal, diagonal, and left. Okay, so the upper one we did I -1. The, the diagonal will do both I -1, j -1, and here we will do j -1. Okay, here we no need to do the +1 because we have handled this condition here. If it's less than 0, it will directly return 0. Okay, and if okay, I think it will return 1. Yeah, we have to return 1 plus again here the same one, math dot min of upper comma math dot min of diagonal comma left. Okay, so our recursion function is ready. Let's make a deep no, we'll not making a deep array here, right? We'll do it later. So for for every index we need to find it, right? So now I should j plus plus. So we'll make here int answer equal to 0. Okay, and for every index call we will do here answer plus equal to find. We will call this function. Okay, ij and matrix, and we will return answer. Okay, let's try to run it. Okay, matrix of ij array required. Oh, I've not given another. Okay, I think now it will work fine. Yeah, that's working. So let's add memoization to it by adding dp int dp equal to new int matrix dot length matrix of 0. Oh, sorry, dot length. Okay, we have made this, and we'll initialize everything with -1. I'll just copy this one from here. Okay, and we'll use arrays dot fill. It will fill every dp of I with -1. Okay, so everything, and here we will pass dp now, dp. Okay, here we are also adding dp of I j equal to. Okay, and we'll add a check here if dp of, we'll add that check here only, dp of I and j is not equal to -1, return dp of ij. Like we have pre-computed it, so we'll directly return it. So in this way we are just adding the memoization here. Okay, the code is same, hope you get it. And let me check if I'm missing something. Okay, okay, I'm missing here, we are not passing dp everything. Okay, here also we need to pass it. Okay, okay, we got it. Let's try to run it now, and we'll try to submit it. So we have seen two solutions, one is iterative and the other is recursive. Both we are using dynamic programming and trying to compute. Okay, so hope you get it. For this also the time complexity and space complexity will be same, that is big of mn. So hope you get it, and I've tried my best to make you understand. If you still have any doubt, you can post it into the comment and try to answer you. Okay, thank you, and like